The first science images from the James Webb Space Telescope are set to be released on the 12th of July 2022, and it's fair to say that excitement levels in the astrophysics community are rising rapidly. Not only are we going to get a data showcase of what each detector on board the telescope can do, but also all the data from early release science projects will also get released. In fact, that data is being taken right now as I film. I've heard from colleagues who said their data is slowly trickling in for one of these successful early release science projects, like, for example, the SEERS survey, which is targeting a huge range of sky to find as many distant galaxies as possible. Now, if you want to see the full list of early release science projects that the data is being made public for on the 12th of July, I'll pop a link in the video description for you to check it out. So the 12th of July is just going to be this big public data dump that's going to allow all the astrophysics community and, any members of the public too, to familiarize themselves with what Webb data looks like and what the telescope is capable of as well. But until then, we have had the odd scrap of data thrown our way by NASA just to tease us. Like this sneak peek of data from MIRI, one of the 4 instruments on board the telescope, which I got very excited when I saw. I think if I'm being honest with myself, I'm most excited for MIRI data. So this sneak peek shows images of a star at infrared wavelengths to show how clear it is compared to the previous data we've had at that wavelength. And even better, a little sneak peek of a spectrum from MIRI, where you split the light through a prism to make a trace of how much each wavelength of light you detect. The red line is a MIRI spectrum of a galaxy showing a big spike due to the presence of hydrogen in that galaxy. And the blue line is data from the old Spitzer telescope of a similar galaxy, not quite the same one, but at the same wavelength range. And that was the best we could do at this wavelength before. Like, look at the difference in resolution. It is absolutely astonishing. And this is where the James Webb Space Telescope will shine, will come into its own. It's got that much bigger mirror that we had to go through that, nail-biting, tense unfolding process earlier this year for. That bigger mirror is the reason it can collect enough light to do this, to pass it to an instrument like MIRI. But why is MIRI specifically so special? Well, MIRI is what's known as an integral field unit instrument, an IFU. So unlike, maybe a traditional telescope that might just take one observation of the sky, one single spectrum of one galaxy or one star or whatever it is, MIRI mosaics up the sky to take many spectrum all at once, so that you get a spectrum at every single pixel. Or another way to think about it is that it's an image at every single wavelength. And that could be a mosaic of one specific object or across a huge swath of the sky. Now, we have instruments like this on telescopes on the ground. For example, I work with data from the 2.2 meter telescope at Apache Point Observatory in New Mexico from the MANGA survey. And I'm hoping to get time to use an even higher resolution IFU on the very large telescope in Chile called MUSE. But those instruments are, first of all, on the back of telescopes on the ground. So they're limited, by atmospheric seeing, the fact the atmosphere distorts the picture. And B, also they're optical instruments as well. They detect visible light that we can see with our eyes, unlike MIRI and James Webb, which detect infrared wavelengths of light. And MIRI is special because it looks in the mid to far infrared region of the spectrum of light at much longer wavelengths than the other 3 instruments on board JWST, so it is especially unique, allowing it to detect the most distant galaxies whose light has been redshifted to the extreme and peer through dust to see planets forming around stars in the Milky Way. So this sneak peek of MIRI data that NASA has just teased us with, right, is from all of the fine tuning and calibration they've been doing to MIRI during the commissioning phase to better understand how it performs and how it behaves. So for example, the images that were released show how for an increasing wavelength from short wavelengths in the top left to long wavelengths in the bottom right, first of all, that the star is in the expected place it's supposed to be on the sky, marked by the circles there. But you can also see on these images how much brighter the star is at shorter wavelengths. That's expected, right? But it's so bright that you actually get this classic diffraction spike pattern of a 6-pointed star. I already made a video on why we get that very specific star-shaped diffraction pattern through the optics of the James Webb Space Telescope. If you want to check that out, I'll link it up here and down below. And then you can see that the star gets fainter at longer wavelengths, so that diffraction diffraction spike pattern disappears, but the background noise increases. That's actually thermal infrared emission from James Webb's hexagonal mirrors themselves. So that's something that people who are intending to work with MIRI data at that much longer wavelength are going to need to be aware of. And then the other calibration step that was done to the spectrum, essentially figuring out which pixel on the detector corresponds to which wavelength. So by detecting a well-known peak where we know that hydrogen emits lots of light at that wavelength, they then had a marker point to calibrate the detector. So that now MIRI is finally taking actual science data for those early release science programs that I'm just so excited to see the data from. You know, they'll know exactly what wavelength of light they are detecting. Now, if you want to know more about MIRI, check out the interview that I did with Dr. Sarah Kendrew from the European Space Agency, who's been involved in the design and development of MIRI and who will be getting her hands on some of the first science data. So while this sneak peek of data might not look like much yet, we have to remember this is just from the commissioning and calibration phase of the mission. MIRI's science data, though, I reckon is gonna blow us all away. Before we get to the bloopers, a huge thank you to Brilliant for sponsoring this week's video. Brilliant is an interactive STEM learning platform that gets you to learn by doing, immersing yourself in a topic so that you grasp those core concepts that are so key for understanding. Learning like this is the way I personally learn best. Now, Brilliant has courses across a huge range of science, maths, and computer science that you can do at home or on the go, but crucially, at your own pace. Plus, if you ever get stuck, there's always more detailed explanations for you to dive into. Now, one of the things I always hear from people, and students especially, is that, I want to be an astrophysicist, but I'm no good at maths, so what do I do? And my answer is always, practice, practice, practice until the maths becomes this second language that you can speak to talk about cool things like black holes. If that sounds a bit daunting though, check out Brilliant's new Everyday Maths course, which goes through the basic ideas in maths in a familiar context, so that although the maths concept might not be familiar, at least the setting is. So if that sounds like something you'd be up for, you can click on the link in the video description down below, or you can head to brilliant.org/Dr. Becky and sign up completely for free. Plus, the first 200 people that go to that link will get 20% off an annual premium subscription. So thank you so much to Brilliant for sponsoring this video. And now, roll those bloopers. Well, this isn't really a blooper, but I completely forgot to say, if you fancy some James Webb Space Telescope merch, check out my merch store that's linked in the video description down below. You can get this, which is the James Webb hexagonal mirror array, but with the reflection of the first alignment image that we got from NIRCam. I'm absolutely obsessed with this. I love it so much. I love the colors so much. So the 12th of July is set to be this huge data dump that will allow the astrophysics community essentially to familiarize, space is hard, it's hard. MIRI's science data though, I reckon is gonna blow us all away. Blow us all away. Gotta get a Hamilton reference in there anytime I can. So unlike traditionally, like with a telescope might just take one observation, like one spectrum of one object in the sky at once, MIRI mosaics I don't know what I said, MIRI mosaics. Did I just merge everything together? I feel like I ended that on a bit of a downy, it might not look like much. It looks like much to me. That spectrum resolution is amazing. But I know that other people look at it and go, is that it? Which makes me sad. Anyway,